Okay, great. Can you guys all hear me here? Yes, good. Okay, so thanks for the lovely introduction, and thanks for inviting me to participate in this awesome symposium. I'm so excited to be here in this very, very large room that we're all in together today. So I'm going to be talking about a relatively new project that I've been working on with my collaborators, Forough Poursabzi, who's in the audience today and is also going to be on the postdoc market soon, and my Microsoft research colleagues, Dan Goldstein, Jake Hofman, and Hanna Wallach. So I would normally start a talk like this with some motivation about why we should care about interpretability. But I think that that's already been covered pretty well today. We've seen a lot of work on interpretable machine learning methods presented today and throughout the whole week here. Right? So when I look at the landscape of research on interpretability, I generally think about it falling into two broad categories of approaches. Right? So one approach to interpretability is to design and deploy models that are somehow intuitively simple. Simple might mean something like a small decision tree or a sparse linear model. The second common approach is to design simple post hoc explanations for potentially complex models. So I would put work like Lime in this category, along with the nice work that Scott Lundberg presented earlier this week, and many, many other pieces of work that we're seeing pop up from the machine learning community. But looking at these approaches, it's natural to ask, what makes a model or explanation simple? And how is this related to interpretability? Right? What does interpretability even mean? And, you know, indeed, there's still a fair amount of disagreement in the research community about what interpretability means and how to measure it. There have been a few recent position papers examining this issue, which I'm sure that many of you have seen, and we've heard a debate about this already on the panel today. I want to add that the question of how to define, quantify, and measure interpretability is not just something that machine learning researchers are thinking about either. So there's an ongoing debate in the legal world as well, since once the GDPR becomes enforceable in the EU next year, companies that use machine learning to make decisions that affect people's lives are going to be legally required to provide meaningful information about the logic involved. But again, it's just not clear what meaningful information means. So my colleagues and I spent a lot of time sitting around gathering up different definitions of interpretability that have been informally used in the literature and trying to make sense of them. As my colleague Hanna Wallach mentioned at the start of the panel earlier this day, we came to the conclusion that part of what makes interpretability hard to define is that interpretability is not something that can be directly manipulated or directly measured. Rather, interpretability is this latent property that can be influenced by different manipulable factors, such as the number of features of a model, whether the model is linear or more complex, whether the model is fully presented to the user or treated as a black box, and even the user interface. At the same time, interpretability impacts different measurable outcomes, such as the extent to which a user trusts a model, a user's ability to debug a model or figure out where it's making a mistake, or a user's ability to simulate the model's behavior. The difficulty of defining and quantifying interpretability is compounded by the fact that there are different types of users, and these users have different needs in different scenarios. So, as Bean Kim also hinted at earlier today when she was presenting this challenge, the approach that works best for a CEO who's making strategic decisions is likely to be different from the approach that works best for a regulator who wants to understand why an individual is denied a loan. And this in turn may be different from what works best for a data scientist who's trying to debug a model. All right, so as if this weren't already complicated enough, let's step back and take a closer look at this picture. So notice that all of these properties on the left, the number of features, whether the model is linear, and so on, are properties of the system design. Right? These are the kinds of things that computer scientists are really good at thinking about and really used to thinking about. So maybe it's not surprising that many of the existing approaches to interpretability focus on that side of the picture. But in contrast, on the right here, we have all properties of human behavior. And now I know that there are some exceptions, but I'd argue that for the most part, computer scientists, and especially machine learning researchers, are not really trained to think about humans, right? This is just not what we do. So this brings me to a central theme of my talk here, and one takeaway point that I really hope will stick with you, okay? Interpretability is not a purely computational problem. Ultimately, what's interpretable or not is defined by people, not algorithms, right? And because of this, we really need interdisciplinary approaches if we want to address the problem of interpretability. This is not something that computer scientists are going to be able to just define and solve on our own. So one of my collaborators on this project is Dan Goldstein, a prominent psychologist with a long history of research on judgment and decision-making. Now, unlike computer scientists, psychologists like Dan are really good at thinking about humans and human behavior. In fact, psychologists and social scientists have been studying trust in models since the 1950s, so more than 60 years. For example, there's a whole literature on the phenomenon known as algorithm aversion, in which people are less likely to trust an algorithm or predictive model after witnessing it make a mistake. The general approach that's used in this literature is to run randomized human subject experiments in order to isolate and measure the impact of different factors on trust. And I think it's very natural to ask whether similar techniques can be applied to interpretability. So the goal of this project that we've recently started at Microsoft Research is to apply this approach, running randomized human subject experiments, in order to understand fundamental properties of human behavior that are pertinent to interpretability. So the idea is that we want to randomly vary these system factors on the left side of this picture and measure the impact that varying these factors has on these human properties on the right side. While this may seem like a simple idea, in practice it can be really tough to do this while holding all else equal. So that's going to be a contribution of our work. I want to just take a moment to contrast what we're doing and what I'm proposing here with the types of experiments that are often included in papers on interpretability, like the well-known Line paper, which are also really useful but different. So rather than focusing on validating or evaluating one specific machine learning innovation, what we're doing here is attempting to isolate and measure the impact that different factors, like the number of features in a model or something else, have in a more systematic way by taking an experimental approach. So this is kind of fundamentally different. All right, so what I'm talking about here is a long-term, somewhat ambitious project, and we're still in the very early stages of it now. But just to give you a flavor of what we're doing, I'll tell you about our first experiment that we ran. So we ran a large-scale, randomized human subject experiment on 1,250 participants who we recruited from the crowdsourcing platform Amazon Mechanical Turk. I should note that it's not only computer scientists who use Amazon Mechanical Turk, but actually it's becoming kind of de facto in the psychology community as well. So in this study, we varied two factors that are thought to make models more or less interpretable: the number of features and whether the model is clear or black box. And we measured how these changes impact trust in the model, simulatability, and prediction error. Since our participants were recruited on Mechanical Turk, we generally wouldn't expect them to have any special technical or domain knowledge. So you can think about this as a study of factors which help lay people make better decisions, gain trust in a model, or uncover places where a model goes wrong. So we're focusing just on lay people here. All right, so in our study, participants were asked to predict prices of apartments in one neighborhood of New York City, the Upper West Side. and they were given a model to help them with this decision. So in addition to a simple baseline in which participants did not have access to any model, we considered 4 experimental conditions in a 2x2 design, corresponding to the 4 models you see here. So I don't expect you to be able to read everything on the screen, but let me point out the differences between the conditions. So the top 2 models use 2 features in their predictions, while the bottom 2 use all 8 features. The models on the left are black box. We don't tell the participants how they work. While on the right, you see a transparent linear regression model with weights that are visible to the participants. And for these conditions on the right, where the internals of the model were visible, we explained during the training phase exactly how these models work. Now I want to emphasize something that's super important to the design of our study here. So in all of these conditions, participants see the same model input, that is the same apartment features, and the same model output, or the same predictions. Okay? That is, we specifically chose apartments where the 2-feature and 8-feature regression models made the same prediction when rounded to the nearest $100,000, which we're doing here. So the only difference at all is what the participants see in between. So this means that if we observe differences between these conditions, then we can safely say that these differences were because of the model. Right, so this is super important. Okay, so after a training phase, in which participants viewed 10 apartments, observed the model's predictions for these apartments, made their own predictions, and then observed true prices, participants entered a test phase. In the test phase, for each new apartment, we first asked participants to guess what the model was going to predict in order to get at how well participants understood the model. And this allows us to compare simulatability between models. We also asked participants to report their confidence in this prediction. Next, we displayed the model's actual prediction and asked participants what they thought the apartment actually sold for. This allows us to assess both their trust in the model and their ability to make good decisions based on the predictions that we gave them. So you may have heard about this replication crisis that's going on in the psychology world. Perhaps you saw this recent cover article in the New York Times Magazine. So in order to promote replicability of results and just good scientific practices more generally, it's becoming really standard now to pre-register hypotheses before running a behavioral study in order to prove that you're not just fishing for results in your data after the fact. So for our experiment, we pre-registered 3 hypotheses using the website as predicted. The first is that our clear 2-feature model will be easiest for participants to simulate. The second is that participants will follow the clear 2-feature model more than the black box 8-feature model. That is, we hypothesized that participants' final predictions would be closest to the model predictions in the clear 2-feature model. Third, we hypothesized that behavior will vary across conditions if an unusual example leads the model to make highly inaccurate predictions. And I'll say a little bit more about this hypothesis in a few minutes. So let's start by examining the first hypothesis. So we define simulation error to be the absolute deviation between the model's prediction and the participant's guess about what the model is going to predict. So here I'm plotting this deviation averaged over all participants in the condition and all apartments for each condition. And we've got here the black box 2-feature model, the clear 2-feature model, the black box 8-feature model, and the clear 8-feature model. And we can see that as we hypothesize, participants have lower simulation error in the clear 2-feature model than they do in the black box 8-feature model. It's about $132,000 on average compared with $239,000. So this is actually a fairly big difference. This suggests that on average, participants in this condition have some understanding of how the model works at least, which is reassuring. Notice that the simulation error is actually highest for the clear 8-feature model, which is the one on the right here. So it's actually not just the transparency of the model that matters, but the number of features as well. All right, so on to hypothesis 2. Is it the case that participants follow the clear 2-feature model more than the black box 8-feature model? In other words, do they trust the clear 2-feature model more? To measure this, we calculate the absolute deviation between the model's prediction and the participant's prediction of the apartment's price. A smaller value here would indicate higher trust in the model. Here I'm showing this for the same 4 conditions: black box 2-feature, clear 2-feature, black box 8-feature, and clear 8-feature. And contrary to our second hypothesis, we actually find no significant difference in participants' trust between the conditions. So this hypothesis actually does not hold for our study. That is, the various models that people would generally assume differ a lot in interpretability, whatever that means, actually all seem to have the same effect on people's predictions. So this is surprising, at least it was surprising to us. Holding accuracy constant, it seems to be a common assumption that people would put more trust in predictions of a transparent model, but we're actually not observing this in this particular study. Relatedly, if we look at prediction error for different conditions, that is, absolute deviation between the apartment's actual price and the participant's prediction, we also see no significant difference between the 4 conditions with the model. The bar on the right here is showing the prediction error for the baseline condition with no model, which is much higher. So having the model around does help people make better predictions, but we're not, again, seeing differences between different conditions here. Okay, so we saw that hypothesis 1 held, hypothesis 2 did not hold in this study. Let's look at the third hypothesis. So here we wanted to test what would happen if the model made a prediction that was bad. Would participants be able to spot the mistake, or would they trust the model? So on the one hand, you could argue that if a user understands the model better, she might trust the model more and thus be less likely to deviate from its predictions. On the other hand, you could argue that if a user understands the model better, she should be better equipped to catch mistakes that the model is making. So we didn't hypothesize ahead of time which way this difference was going to go, just that there would be a difference there. So the linear regression models that we trained to predict these apartment prices happen to place a very high weight on the number of bathrooms. So they're saying each bathroom is worth $350,000, which works well on most of our data. But so at the end of the study, we showed participants 2 apartments that have an unusually high number of bathrooms for which the model would make a really bad prediction. Right, so the apartment that I'm showing here is a 1-bedroom, 3-bathroom, 726 square foot apartment, which is clearly very strange, and the model is predicting that it's worth $1.5 million. So we would hope that participants, especially if they're actually able to see the model internals here, would be able to spot this mistake. So here again, I'm going to show the participants' deviation from the model. If people know when not to trust a model, we should see larger deviation or higher bars for the clear models. But we don't see that actually. We see something that looks almost the opposite. Right? So, for example, participants who saw the clear 8-feature model here deviated from the model about $60,000 less than participants who saw the black box 8-feature model. So somehow, participants who are able to see the model internals are kind of trusting the model more, even though it's making a mistake. So I gave a talk on this work with some preliminary results about a month ago, and someone in the audience raised a concern that, perhaps participants aren't able to spot examples where the model was wrong because New York housing prices are just generally so nuts, like they all look crazy. So to check this, we very recently, just this week actually, ran a variant of our study with prices scaled down to be on par with the median US housing prices, just to see if this would change anything. We again pre-registered hypotheses for this new study. The first 2 that we pre-registered were the same as in our first study. The third we made a little bit more precise based on both what we'd observed in the first study and some observations from a small pilot that we ran with scaled down prices. So in particular, we predicted that participants would deviate less from the clear models than the black box models on these unusual examples. Okay, so let's see what happened this time. So reassuringly, the first hypothesis continues to hold. We see the same trend with simulation error. Again, participants are better able to simulate the clear model with 2 features. They do actually a little bit worse at simulating the clear model with 8 features than any other. Same thing we saw before. So what about the second hypothesis, that participants follow the clear 2-feature model more? Well, just like in the first study, we saw that this hypothesis didn't hold again. So it wasn't just the kind of outrageous New York crisis that were making this hypothesis fail. We again see, very similar results for how much participants' predictions deviate from that of the model, though maybe the deviation from the clear 8-feature model is very slightly higher here. And there's still just not a big difference between conditions. Participants trust all of them about the same amount. And we also see similar trends for prediction error to what we saw before. So what about this third hypothesis? So our results show that the third hypothesis does indeed hold. So participants deviate less, again, from the model in the clear condition than they do in the black box conditions on these unusual examples. Now, I think that this example is really interesting here. Participants in the clear condition are able to see that the model is placing a large weight on the number of bathrooms. If they know anything at all about real estate, this should really raise some red flags to them when they see this small apartment with 3 bathrooms, but they still trust the clear model more. So it would be really interesting to get some future work looking into why this might be the case. And I should say that this also comes out in self-reported measures of trust. Participants in the clear condition also report trusting the model's prediction more on this particular bad example. So we asked them this just about this one example, and they also report trusting the model more here. Okay, so to summarize the results of this study, as we hypothesized, participants are better able to simulate the clear 2-feature model compared with the black box 8-feature model. However, we didn't see any significant difference in participants' deviation from the model across conditions, meaning that on most examples, participants actually trust the models equally. This kind of goes against the widespread belief that more transparent models will lead to better predictions, or that people will trust them more, right? So in addition, there's some belief that clear, transparent models will lead people to understand when they shouldn't be trusted. But actually, when we show participants a weird example in which the model is wrong, participants in the clear condition deviate from the model less than those in the black box conditions, despite the fact that they're able to see the weights that the model is using and could potentially detect the error. Not only did they not pick up on the problem, but they may have actually trusted the model more in these cases. So of course, there are many more questions that we could have asked here. There are many more studies that we could run. And as I said, this is all still work in progress. We chose to vary just a few of these system properties on the left and to measure just a few types of human behavior on the right here. There are many more. We only looked at lay people. We only touched on a few squares in this grid that I put up before. Maybe we need to be expanding this grid. But I view the work in this talk today as one first step towards a larger interdisciplinary research agenda aimed at quantifying and measuring the impact of factors thought to make machine learning models more or less interpretable. So I want to close by returning to the central theme and takeaway point that I mentioned earlier in the talk. Interpretability is not a purely computational problem. We just can't ignore the fact that there are humans in the loop here. And we therefore need interdisciplinary approaches in order to address it. And this is a space where I think that there's a lot of room for future work, and I hope this is something that people will start getting excited about. Thank you. people have questions, they can come up to the mics.
He's introducing Jerry, right?
Oh, right, sorry, I was thinking
there is a lot of effort toward infographics now. So I wonder if, for instance, seeing that that point was a stream point, so giving information about the domain together with just the machine providing the answer would change the position. So we're making a lot of efforts for making, say, data science interfaces at all the different users you were listing. So is it possible there is also a potential for, let's say, pseudo-physical interaction with the data that can help modifying some of your results?
So I'm not positive I understand what you're asking. Are you saying, like, is it possible that if we, let these users play around with the data more and see what the model is doing?
Just seeing the data. So, for instance, you see some graphical representation of the distribution of the data. So you see that your data is spatial. This rings a bell, and perhaps you're going to use your tools differently.
Yes, definitely possible. I mean, this is not something that we've explored at all, but I can absolutely imagine that various tools for visualizing the data and exploring it would help. In our particular study, which is all that I can really comment on, I can't speculate on anything else, the only opportunity that users had to play with the data was in this training phase where we just gave them a series of examples and kind of let them see what the model was going to predict and let them see true prices. So they got to play a little bit in that way, but it was a small number of examples. They didn't get a sense of the general distribution and so on. So absolutely possible.
Hey, over here.
Oh.
Hi. So first of all, thanks a lot for your very insightful study. I think it has a very important feature, namely that the people participating in the study might have an understanding by themselves about what influences the price and in which way. And it's probably the feature that you use in order to measure trust, whether their own understanding matches the model. In my career so far, I've also seen several situations in which humans have no previous knowledge about the influences and what a model could be like, and they want to study things they have not understood previously. How would you address interpretability in such scenarios?
So the first thing I'll say is that we definitely did pick this particular domain because it had this feature that you said. People should be at least roughly familiar with it, although I would expect that we would quite possibly see very different results if we were running this study on real estate agents in New York instead of just lay people on Mechanical Turk, because they would have even more domain expertise. And actually there's kind of an interesting body of work in the psychology literature that looks at how people's trust in a model, a predictive model like this, depends on how much of an expert they consider themselves. So all of that is very important. We haven't thought yet about how to address the kind of scenario that you're talking about, where people are just not familiar at all with the features and don't have an intuitive understanding. I mean, actually, another kind of component or another property that you can imagine having on the left side of the picture that I had up earlier is something about just how understandable the features themselves are, right? Like if people understand the features, that maybe influences this latent interpretability of the model. So I guess in this work, we're not really in the game of proposing new solutions to interpretability. We're not trying to, propose new algorithms in this work. We're just trying to understand how various properties affect, various properties of the system affect human behavior. But you could imagine, running the same types of experiments in other domains where the features are more obscured. And we had actually talked at some point about running the same experiment, but instead of saying number of bathrooms, number of bedrooms, square footage, etc., saying feature X, feature Y, feature Z, and seeing how this changes things.
Yeah, but I'm not necessarily referring to a situation where you don't understand the features, but where you have no previous knowledge about how they influence the outcome.
Yeah, well, I mean, that would get at some of that, right? If you don't know what the features are, then you have no previous knowledge of how they influence your prediction. But
thank you.
Very interesting work. I have one question. I guess your clear 2 and clear 8 conditions is the case where you would explain to the subject what the models are. I was just wondering, do you know if they actually trust your explanation?
if they trust our explanation, that's an interesting question. I mean, if they wanted to, they could take out a calculator and check it. I mean, we're telling the truth in our explanation. But no, we haven't looked at that at all. That's an interesting question.
It's just like if we explain anything at all and pretend it's a planet, maybe people would trust us. That's not a good thing. Thanks.
Very interesting work. Thank you. I was wondering how incentives worked for the workers. Were they incentivized to actually get good accuracy, or were they just, potentially just trying to finish the task as soon as possible, and they were just going with the model? Is that a possibility, or is that a concern?
Yes, so that is a good question, and that's something that we actually debated heavily before running the study, because you can imagine that if you rewarded people based on the quality of their predictions, then they would have more motivation to, put in lots of extra time and try to make really good predictions and all of this. On the other hand, we had some fears because we were running the study online that if we rewarded people based on their predictions, people might, collude, talk about the experiment, influence each other. And we also had concerns because when we wanted to get at simulatability, like how well people can actually, predict what the model is going to predict. When we were thinking about this, we didn't really want people to be like sitting there with a calculator, like really trying to work out precisely what the model was going to do. We wanted to get a sense of how they would kind of look at these things and in their head try to simulate the model. So we also wanted to avoid giving people incentives to actually like sit down, especially in this 8-feature model, with a calculator and try to like figure out exactly what the model is going to do. So in the end, we chose to pay everybody a flat fee for doing the experiment and not reward them based on quality, which is kind of a debate between the psychology community and economics community here. My collaborator, Dan, is a psychologist, so he insists that this makes no difference, and on mechanical turk, people will basically do the same in studies whether or not you incentivize them, which economists don't necessarily agree with, but that's what we ended up doing here. And you can totally imagine that maybe if we were in a scenario where people had a little bit more intrinsic or extrinsic motivation, they might try harder.
Thanks for the talk. I think this is a very interesting area. So I was just wondering if you have thought about or could comment on the case where the clear model that you're showing the user is accurate and gives good predictions, but clearly has some dependencies in it that are incorrect. And so I would expect in that case, maybe the user can still understand what the model is doing and correctly predict its output, but the trust may not be there because they can see there's something clearly wrong with the dependencies the model has found. And have you thought about that at all, or what other metrics you might introduce in order to look at that case?
So we haven't thought about that, but I could imagine running, or I should say we haven't actually run anything that would get at that question, but you could easily imagine doing the same thing, but having some dependencies like that in the model. And actually, I mean, with our model, it was a very good model on this data, but it did have some weights that, if you just look at that weight in isolation, kind of looks like it's going in the wrong direction because, maybe the weight on square footage is somehow adjusting for the weight on number of bedrooms or something like this. So one might be negative. So I can totally imagine that people would lose trust in the model if they see something like that, even if it's a really good model.
Maybe just one more question while Jerry comes and sets up.
So on the theme of the conference that of bringing rigor back into NIMS, and also following on kind of points that you and Hanna have made about using good social science practices, I thought one thing that was really unusual and kind of refreshing in your talk was pre-registering hypotheses. And this is unusual in a community where very often hypotheses are produced after the evidence has arrived. So I was wondering if maybe you could just, from your perspective, between computational and social science, like give us a perspective on this practice and like how to do better science.
Sure. Is this on? Yes, you can hear me. Yeah, so I actually, at first I wasn't going to mention that we pre-registered these hypotheses because it seems like a small detail, but I thought it was actually important to mention in this audience because maybe it is something that people don't think about a lot. But this is actually something that's relatively new in the psychology community too, and it's just coming up in the last few years because there have been all of these very well-known studies that were discredited because people weren't able to replicate them, and it turned out that just, it wasn't anybody's fault necessarily, just the norms in the community weren't what they should be, and people didn't quite understand how bad it was to be fishing for results in their data in the way that they were. So this is something that has really just started happening in the psychology community within the past couple of years, but it is this concerted effort within that community to try to make things more rigorous and try to make sure that results that people are finding are real, and I think it's a really great thing to do. I also actually found it very useful from the perspective of designing our experiment because, it's so easy a lot of the time to kind of have a vague idea of what you want to do and run an experiment and then be like, oh, well actually we didn't quite get the data that we need to answer this other interesting question because we didn't think about it, or oh, we can't actually analyze this in the way that we thought that we were going to analyze it because we didn't think it through carefully. So I actually thought it was super valuable to us in the research process to be forced to kind of sit down and write down, okay, exactly what kind of analysis are we going to do? What are we going to predict? Are we going to have the right data for that? Is there any other data that we should be collecting instead, or the different questions we want to ask, and so on. So I think it's a great thing to do both for scientific rigor and just for making sure that you're kind of getting the data that you need and thinking things through. I think I'm overrunning my time. So.
Let's all thank Jenn again.